Bismillahirrahmanirrahim. Dear students, this is 8th lecture of numerical analysis. In the last lecture, I talked about the splines, and then discussed in detail what the cubic spline is and what is the purpose of this spline. Now I will like to have an example how to construct the splines using the definition. So you saw in the last lecture we discussed the definition in detail. There were certain conditions, there were 6 conditions for the cubic splines. So today is the target to use those conditions, how we can construct the cubic spline. For this purpose, I will consider an example. Question is, construct the cubic splines for the given data using the definition data is given to you. Is given by this these values. You can see in this case, this is x0, x1, x2, x3. We are having 4 data points. So according to the criteria of the cubic splines, we can construct 3 cubic splines. What is the form of the spline? That is given by this relation. In this particular example, the value x0, x1, x2, x3, the value of n is equal to 3. It means that you will have s0, s1 and s2 because 3 minus 1 is equal to 2. We will be constructing spline between these 2 points, another spline between these 2 points, and another spline between these 2 points. So let's see that the spline between 0.1 and 0.2 in this interval, the spline is given by, I represented that spline by S0, means that let's replace J by 0. So you will have A0, B0, C0, D0, and this will be x0. The value of x0 is 0.1. So you can see I replace x0 by 0.1. In this case, x is the variable and the value of x lies between 0.1 and 0.2. The spline between 0.2 and 0.3 is given by this relation, and I denoted that by S1. So let's replace this j by 1. When j is equal to 1, you are having S1. This will be A1, this will be B1, this will be C1, this will be D1. And this point will become x1. The value of x1 is 0.2. So you can see I replace xj by 0.2. This is the second spline. The third spline is between 0.3 and 0.4. And that is given by this polynomial. You can see when I replace j by 2, so I represented this spline by 2, s2. So j is equal to 2, j is equal to 2, j is equal to 2, and j is equal to 2. You are getting d2. And this will become x2. The value of x2 is 0.3. So you can see that I replace xj by 0.3. These are the 3 possible splines which we can construct for this data. Now if you look at this data, in every spline there are 4 constants to be determined. So overall there are 12 constants to be determined. A0, B0, C0, D0, A1, B1, C1, D1, A2, B2, C2, D2. These are the unknowns to be determined. So since here are 12 unknowns, so we need 12 equations to complete this system. And for this purpose, we will apply the basic definition, the conditions which were. The first condition was The first condition is given by this relation. You can see that S naught passes through 0.1 and 0, these 2 points. So definitely when I replace x by 0.1, I should get this value. And when I replace x by 0.2, I should get this value. Similarly, S1 passes through these 2 points. So when I replace x by 0.2, I should get this value. When I replace this by 0.3, I should get this value. Similarly, S2 passes through these 2 points. So when I replace x by 0.3, I should get this value. And when I replace x by 0.4, I should get this value. I will be using the initial point in these 2, and I will be using both points in S2. The reason is because this is the initial point, this is the final point, but there is no any other spline which can cover this one. So that's the reason I will be using both of them. Let's go to the first spline. Replace x by 0.1. When you replace x by 0.1, so you will see that this portion will become 0 and we will left with a naught. A naught is equal to f of 0.1 and f of 0.1 is given by this value. So we got the value of a naught. Similarly, let's replace x by 0.2 and S1. And when we replace x by 0.2 and S1, we are getting f of 0.2, which is this value. So when you replace this x by 0.2, this portion will become 0 and we will left with a1 only, and which is equal to f of 0.2, and f of 0.2 from the data is given to us, which is minus 0.28398. Similarly, let's come to S2. Replace x by 0.3. When we replace x by 0.3, you can see that all these values will become 0. And you will be left with a2 only. And a2 is equal to f of 0.3, and f of 0.3 is 0.0000. So we got the value of a naught, a1, and a2 in all these 3 splines. Since there are 12 unknowns, we computed 3, so 9 unknowns are remaining. And for that reason, we need 9 more equations. So let us use the endpoint and S2 because S2 passes through these 2 points. So when I replace x by 0.4, I should get f of 0.4. Replace x by 0.4 over here. So this will become a2. This will be 0.4 minus 0.3, which is 0.1. 0.4 minus 0.3, which is 0.001 because there is square. 0.4 minus 0.3 is 0.1. A whole cube will give you 0.001, and that is d2 is equal to this value. Now if you look at this, the value of a2 already we have computed. So let us substitute this value in this expression. So this a2 will shift to the other side, and we will end up with this equation. So what I did, I shifted a2 to the other side, and then this value minus a2 gives us 0.2418. So far we got 4 equations. Let us go further. This was the second condition. If you look at it, and this is the continuity condition, there are 2 consecutive splines coincides. 2 consecutive splines coincides. So you know that this is another condition of the splines, and that's related to the continuity of the splines at the common point. You know that it's not S1, S2. We have defined these splines in this way. When j is equal to 0, this will be j plus 1. This is S and j plus 1. This is is j plus 1. So when j is equal to 0, so S0 and S1, and the common point will be x1. So when you replace j by 0, so you are getting the condition S0 at 0.2 coincide with S1 at 0.2. And when you replace x by 0.2, so you can see that this portion becomes 0. And that's why you can see A1 on this side. And this will become A0 plus 0.2 minus 0.1 is 0.1 B0, which we can see here. 0.2 minus 0.1 whole square. So 0.1 whole square is 0.001 C0, or plus 0.2 minus 0.1 whole cube. So 0.001 D0 is equal to A1. Since the value of A1 and A0, they are known, so let us substitute these values. So when you substitute these values, so A1 minus A0 is given by this value. So we got another equation, which is equation number 5 at the common point. Similarly, S1 and S2 coincide at 0.3. When you replace j by 1, so this is S1 and this is S2 then. When you replace x by 0.3, so you can see that this portion will become 0 and you will left with A2. That's the reason you can see A2 on the right hand side of your equation. And similarly, when you substitute x is equal to 0.3, so this is A1. 0.3 minus 0.2 is 0.1 B1. This is 0.1 whole square C1, and this is 0.1 whole cube D1. So this is another equation which we got. Since the value of A2 and A1, they are known, we have computed at the beginning. So when we substitute these values, so we end up with equation number 6. So 0.1 B1, 0.01 C1 and 0.001 D1 is equal to A2 minus A1 is given by this quantity, which is equation number 6. This was continuity on the spline. Now let's go for continuity. Go for continuity of the derivative of the function. So again, this is not j, this is j plus 1. This is the mistake, typing mistake, I will say. This is j plus 1. So when you replace the value, x is equal to 0.3. So you can see that what will happen to these equations. Again, when j is equal to 0, so 0.2 is the common point, and we get this equation. 0 is not prime at 0.2 coincide with S1 prime at 0.2, and that gives us, when you replace x is equal to 0.2 here, so this portion will become 0 and you will left with B1, which you can see over here. And similarly, when you replace x by 0.2, so this will become 0.1, this will become 0.1 whole square, and that's the reason you can see B0 plus 0.2 plus 0.03 D0 is equal to B1. And if you rearrange this one, so I shifted this B1 to the left hand side, so we got another equation. Let's come to the second common point, which is 0.3. So when j is equal to 1, so this is S1, this is S2, and this will become x2, and x2 is equal to 0.3. So it coincides according to this condition. When you replace x is equal to 0.3, so this portion will become 0 and we will left with b2, which is appears on the right hand side. And when you replace x by 0.3 over here, so this will become 0.1, this will become 0.1 whole square. And if you simplify this one, this will be b1 plus 0.2 c1 plus 0.03 d1 is equal to b2. And if you rearrange this one, you are getting, so what I did, I shifted b2 to the left hand side, and this is equation number 8. Out of 12 equations, we got 8 equations. Let's come for another condition, which is the continuity condition of the second order derivative in case of the cubic spline. So the common point x is equal to 0.2. These are the second order derivative. You can see if you differentiate it's not, you are getting this one, and when you differentiate this one, you are getting the second order derivative given by this this expression. When j is equal to 0, again this is a j plus 1. Sorry, this mistake in the at x is equal to 0.2. Second is not at 0.2 coincide with S1 at 0.2. So when you substitute the value here, this term will become 0 and we will left with the 2c1. So 2c1, and when you substitute the value here, this will become x is 0.2 minus 0.1 is 0.1. So 2c0 plus 6 into 0.1 d0 is equal to c1, and taking 2 common and cancel that out, so we end up with this equation, and transferring c1 to the other side, we get equation number 9. Similarly, when we substitute j is equal to 1 in this expression, so is double prime 1, x2 is equal to is double prime 2 at x2, and x2 is 0.3, so you are getting this relation. When you substitute x is equal to 0.3, this portion will become 0, you are getting 2c2, which you can see over here. I have cancelled 2 throughout, and when you substitute it over here, you are getting 2c1 plus 6 into 0.1 d1 is equal to c2, cancelling 2 throughout. So we end up with this relation. Now transferring c2 to the left hand side, we get equation number 10. So you saw that I used the condition of continuity of the spline, its derivative, its second order derivative, and you can see that we got 10 equations. There were 12 unknowns, we got 10 equations so far. So 2 equations are remaining. 2 equations are remaining. There are 2 kinds of splines. One is the natural splines and claimed splines. So let us discuss both of them. First, I consider the natural splines. So you know that in this case the boundary conditions are given to us, and the conditions are S0 at x0 prime is equal to f prime at x0. S0 double prime at x0 is equal to 0, and Sn minus 1 double prime at xn is equal to 0. These are the second derivatives I am putting in front of you. S0 at x0, x0 is 0.1 is equal to 0. So when you substitute x is equal to 0.1, so this portion will become 0, and we will left with 2 c0 is equal to 0, which gives us c0 is equal to 0. And the condition on S2 at xn is 0.4 in this case, is equal to 0, and when you substitute the value over here, this will become 0.4 minus 0.3, which is 0.1. So 2c2 plus 6 into 0.1 d2 is equal to 0, and let's cancel 2 throughout. So we got two more equations, equation 11 and equation 12. So you can see that for this system we need 12 equations, and we got 12 equations using the different conditions. So this is the case of the natural splines. We completed our system. Now let's solve this system. You can see I have written these except the first three: 1, 2, 3, 4, 5, 6, 7, 8, 9. Three equations were A0, A1, A2. So already these quantities are known. So let's find out the rest of the 9 quantities. So I have rearranged this system. So now let's write this system in matrix form. You can see this is the matrix form. Look at this one. This column is for the coefficients of B0, C0, D0, B1, C1, D1, B2, C2, and D2. So for the first column coefficient, let's come to this equation. The coefficient of rest of the constants coefficient is 0, except the coefficient of C0 is 1. So the coefficient of C0 is equal to 1, and the rest of the coefficients are 0 of these values. On the right hand side, you are having a 0. Let's come to this one. Coefficient of B0 is 0.1. Coefficient of C0 is 0.01. Coefficient of D0 is 0.001. And rest of the coefficients are 0. So you can see rest of the coefficients are 0. And this is equal to 0.3651, which is on the right hand side. Come to the third equation. Coefficient of B0, C0, let's look at the third equation. The coefficient of B0 is 1, the coefficient of C0 is 0.2, and the coefficient of D0 is 0.03, and the coefficient of D1 is -1. Rest of the coefficients are 0, and this is equal to 0. You are having 0 on the right hand side. Now let's come to this equation. Coefficient of B0 is 0, coefficient of C0 is 1, coefficient of D0 is 0.3, coefficient of B1 is 0, and coefficient of C1 is -1, and the rest of the coefficients are 0, and that is equal to 0, which is another equation. Now let's look at this equation. In this case, coefficient of B0, C0, D0, they are 0. B0, C0, D0, they are 0. Coefficient of B1 is 0.1. Coefficient of C1 is 0.01. And coefficient of D1 is 0.001. And the rest of the coefficients are 0. And that is equal to 0.2906. That's another equation. Now let's come to the next one. So you can see in this equation also the values of the coefficients of B0, C0, D0, they are 0. So you can see them over here, and the coefficient of B1 is 1, coefficient of C1 is 0.2, the coefficient of D1 is 0.03, and the coefficient of B2 is -1. The rest of the coefficients are 0, and right hand side is equal to 0 also. Come to the next equation. Coefficient of B0, C0, D0, B1, C1, D1, they are 0. And you can see that these are the coefficients, they are 0. Coefficient of B2 is 0.1, coefficient of C2 is 0.01, and coefficient of D2 is 0.001. and right hand side it's 0.2418. This is the last equation, and if you look at this equation, in this case coefficients of B0, C0, D0, B1, C1, D1 and B2, they are 0. Coefficient of C2 is 1, coefficient of D2 is 0.3, and that is equal to 0 on the right hand side. So you can look at this system. This is the matrix form Ex is equal to B, where this is the coefficient matrix, and you saw that how we got this coefficient matrix. This is the matrix X, which is the column matrix containing unknowns, and these are known the right hand side, which normally we represent by B. So I can write this in the matrix form Ex is equal to B. So you can see it over here, and when you pre-multiply with E inverse both sides, so E inverse into A will become identity multiplied by X is equal to X, and this side will become A inverse B. Remember, matrices are not commutative in general, so you have to be careful. You have to be careful. Since I multiplied E inverse from left hand side, that's the reason you can see I'm writing that from left hand side. And now you are having X is equal to A inverse B. You know how to find out A inverse, that you know from your matriculation, that how you can find out the inverse of this matrix. You can find out the inverse of this matrix and multiply with matrix B. You will get these unknowns which you are looking for. Yeah, you can use the Kramer rules, because this is a 9 by 9 system matrix. You can use the Kramer rule, you can use the Gaussian elimination technique, you can use the Gauss-Jordan method, and that will give you the values of X which I have solved, and the values of X are given by. So you can see that I got values of B0, C0, D0, B1, C1, D1, B2, C2, D2. And you can see that these are the values which we were looking for. We solved the system, got these values. Now the target was to construct these splines. So let us see. These were the splines, S0, S1, S2. This spline was defined between 0.1 and 0.2. This spline was defined between 0.2 and 0.3. And this spline was defined between 0.3 and 0.4. So just substitute the values of A0, B0, C0, D0 over here. You are getting these values. You can see this is the value of A0, this is the value of B0, C0 was equal to 0, and this is the value of D0. Similarly, the values of A1, B1, C1, D1, if you substitute in this equation, you are getting this is the value of A1, this is the value of B1, this is the value of C1, and this is the value of D1. So this S1 is coming from here, and when you replace the value of A2, B2, C2 into D2 and S2, you are getting these values. This is the value of A2, this is the value of B2, this is the value of C2, and this is the value of D2. Now these were the splines we were looking for. So what we did, we replaced the data which already we had, we replaced the data by smooth and continuous curves. Remember, S0 and S1, they coincide at 0.2. And similarly, S1 and S2 coincide at 0.3. So this gives us a smooth and continuous curve. Now, if you are looking for the value of the function at the point which lies between 0.1 and 0.2, somewhere between 0.1 and 0.2. So replace X by that value in S0, you will be getting the approximated value. Similarly, if you are looking for a value of the function which lies at a point which lies between 0.2 and 0.3, so replace X by that value in S1 and you will be getting approximated value of the function at that particular point. And similarly, if you are looking for the value of the function at the point which lies between 0.3 and 0.4, so replace x by that value in S2 and you will be getting the approximated value of the function, which is the interpolation you were looking for. Now, if I plot S0 between 0.1 and 0.2, hold on the figure, plot S1 between 0.2 and 0.3, and plot S2 between 0.3 and 0.4, you will see that you are getting this smooth and continuous curve. So you can see it starting from 0.1 and reaches up to 0.4. You can see that this is your curve which you are getting from this spline, and you can see that this is a continuous curve. Remember, these are the splines which we got using the free boundary conditions. Means that S0 double prime at x0 is equal to 0 and S2 double prime at xn is equal to 0. You got the curve? You can do the interpolation. Now let's come to another case. The claimed splines. Remember, I told you the last two equations in the previous case. The last two equations, they were coming from the naturally free boundary conditions. Claimed boundary conditions, if you remember, there will be only change at the boundary conditions. The rest of the system will be the same. It means that you got the first 10 equations will be the same. Only change will occur in equation number 11 and equation number 12, because you know that in case of claimed splines, S0 prime at x0 is equal to a prime at x0. If that is the case, replace x by 0.1, so you can see that this portion will become 0. And you will be getting B0. B0 is equal to f prime at 0.1. Remember, this quantity is given to us, and that is the value of f prime of 0.1. If it is not given, so inshallah in the next chapter we will be talking about the derivative, from how we can find out derivative of a function at the given data points. So it will be given to you. If it is not given, then after the next chapter you will be in the position to find out this derivative from the data. So you can see that you got the value of B0 from here, which is straightforward from here. This portion is equal to 0, B0 is equal to a prime of 0.1, a prime of 0.1 is given by this quantity. Similarly, you will have this is S2, not S1. This is not S1. This is S2. S2 prime at 0.4. You can see this will be B2. This will be B2. 0.4 minus 0.3 is equal to 0.1. 0.1 multiplied by 2 is 0.2 into C2. And similarly, this will become 0.4 minus 0.3, which is 0.1 whole square. That is given by 0.01. And 0.01 multiplied by 3 is 0.03. D2 is equal to, this is the given value, f prime at 0.4. So you can see in previous case you got 10 equations. Instead of the natural spline, use the claimed spline, the conditions, you got 2 more equations. And now you can see that what will be the matrix form. This is the system I have rewritten, except the first equation and the last equation. The rest of the equations are the same as we got in case of natural or free boundaries. So let us write this in matrix form. You can see that this portion is the same as we discussed in case of natural splines, except the first and the last. So you can see the coefficient of B naught is 1 now, and that is equal to 3.5850. And similarly, in the last case, coefficient of B naught, C naught, D naught, B1, C1, D1, they are 0. And you can see that I have replaced these coefficients by 0. Coefficient of B2 is 1, coefficient of C2 is 0.2, and coefficient of D2 is 0.03 is equal to, this is the right hand side. So you can see I highlighted, I put that in the red. Only these first row and last row they change, and the rest of the matrix is the same. Why this change occur? This change occur because of the claimed splines. So if you are using the claimed spline, the rest of the system will be the same except the boundary conditions. So these two conditions are different from the conditions which were in natural splines, and that's the reason you can see the first and last row, they are different in this case. Again, in matrix form, this can be written as Ax is equal to B. Coefficient matrix, I denoted this coefficient matrix by A. This is the variable matrix, column matrix, I represented that by X, and the right hand side, these are the known quantities from this system, which is given by B. And again, you can find out the inverse of this matrix and can find out the values of unknowns. B naught, C naught, D naught, B1, C1, D1, B2, C2, D2. So you can see that slight change is here in the values of these unknowns. Once we have computed these unknowns, now we can construct the splines. So these were the splines. But remember, this time the conditions were different, and that's the reason you can see that some of the values will be different. A naught, the same is the previous A naught, A1, A2, they are the same. The rest values have been changed. So let's replace the values of A naught, B naught, C naught, D naught, and S naught. You are getting this one. The x lies between 0.1 and 0.2. This is the value of B naught, value of C naught, value of D naught. You saw in case of natural spline, this coefficient was 0. But now you can see this is not 0. It's different from that one. This is because of the condition. S1, replace the values of A1, B1, C1, D1. A1 is the same as previously. This is the value of B1, B2, B3 in the previous slide. And similarly, put the values of A2, B2, C2 in S2. You are getting this spline. This is the same as in case of natural, but this is the value of B2, the value of C2, value of D2 in this case. So you can see that if we are having claimed splines, again we replace the data by a smooth and continuous curve. Now again, if you are want to do some interpolation, if the value of you want to find out the value of the function at a point which lies between 0.1 and 0.2, so replace that value of x in S naught and you will be getting the corresponding approximated value of the function. If your interest lies in the value of the function at a point which lies between 0.2 and 0.3, then you have to replace x by that quantity in S1 and you will be getting approximated value of the function. Similarly, if your interest lies in the value of the function at a point, value of x which lies between 0.3 and 0.4, so replace this x by that value and you will be getting approximated value of the function using the claimed boundary conditions. Again, if you plot S naught between 0.1 and 0.2, hold on the figure, then plot S1 between 0.2 and 0.3 and plot S2 between 0.3 and 0.4, you should get a smooth and continuous curve, which you can see over here. So you can see it starting from x is equal to 0.1 and it reaches up to x is equal to 0.4. And if you look at the curve, this is a continuous curve, and that was the claim of the splines. So what you did, you replace the data by the polynomials in natural spline using the natural conditions, using the claimed boundary conditions. In both the cases, your curve is a continuous curve. So now you can see if you are having more points, you will have more splines, and then you can study your curve, your data. Study of the curve means study of your data, and of course your data is maybe some experimental data. You might have collected the data from the field and you replace the data by mathematical expressions. You replace that by a curve, and then you can study whatever you like. For example, you are looking for the integration of your data between the initial point of the data and final point of the data. So f of x dx limits from 0.1 to 0.4 will be equal to integration of s of x dx limits from 0.1 to 0.4, and now according to the criteria of the calculus you have to split them in three parts. That will be equal to integration of s0 from 0.1 to 0.2 dx plus integration of s1 from 0.2 to 0.3 dx plus integration of s2 from 0.3 to 0.4 dx. And you can see that you can do the integration very easily. Its integration will be just a change will occur. This multiply by x, this multiply by x minus 0.1 whole square divided by 2, minus this multiply by x minus 0.1 whole cube divided by 3, minus this multiply by x minus 0.1 whole raised to the power 4 divided by 4, limits from 0.1 to 0.2. Similarly, limits of this quantity, limits of this quantity. And that will give you the integration of the function from 0.1 to 0.4. It means that will be the area under the curve. So it means that you are looking for the area of this region which lies between this axis, this curve, this line, and this line. So you can find out the area when you have data points. So I hope that this will help you, and I will tell you again, this is very important. It can be used for the solution of ODEs and PDEs also. Try to understand and clarify the doubt if you have. I will be happy to clarify your doubts. Thank you very much.